It'll benefit somebody. It'll hopefully benefit the folks that are not here. Maybe others as well. So like I said, this is kind of the final big topic, and we're going to explore it from a lot of different directions, but it's called the net change theorem. And I think I can prove this to you pretty conclusively, so kind of pay attention. I'll show you a couple things here, and we'll jump into some applications, and hopefully have some fun with this. This is where we can like apply these skills to like actual physical objects or situations that are somewhat realistic. So here's the basic premise right here. The definite integral of a rate of change gives the net amount of change. So let's talk real quickly about units. Rate of change. What kind of units come to mind when you hear rate of change? Meters per second. What else? Feet per second. Can we get out of linear motion? What other units indicate rate? Gallons per hour, units per minute. Donuts per hour, like Billy or whatever. Yeah, that one example. Say again. I'm gonna go happy here and say pizzas per hour. Feels like a pretty happy rate to talk about. Ice cream cones per second. Donuts per minute, like that. Yeah, that one. So, what characterizes a rate unit?
Per time?
Over time.
Yeah, usually it's like a quantity per a time, right? So number of pizzas per hour, number of miles per hour. It's quantity divided by time. That characterizes a rate unit. What characterizes an amount unit? So we just talked about rate units. What about an amount unit? Quantity, no time. Not divided by time. So how about just pizzas? So if I said, think about the difference in these two statements. If I told you guys that I eat 3 pizzas a day, that means one thing, right? But if I just said, I've eaten 3 pizzas, that's just an amount. It doesn't say the same thing as the rate does, right? If I told you that I ate 3 pizzas a day, might you fear it for my future health? Well, wait until you move past age 25 or 30, and you'll understand. Yes, you're all teenagers. Maybe that doesn't matter as much right now. What if I told you that I ate 20 donuts per hour? Might you think that I have maybe a blood sugar problem? Possibly, right? But what if I told you that I've just eaten 20 donuts in my whole life? I've just eaten 20 donuts. That's just an amount, right? That would have a very different feel, wouldn't it? 20 donuts, that doesn't seem like that much when you talk about your whole life. When you talk about 20 donuts per hour, that specific rate, that feels very different. So rates versus amounts, they're related, but they're not the same. One of the ways to relate them is this net change theorem. So let's take a look at velocity for a second. It says the definite integral of the rate of change gives the net amount of change. And so let's go back to what we talked about in the past, velocity. What is the integral of a velocity function? A position function, right? So I want to show you how this works. We'll talk about the units as well. I'm going to show you this in a way that, I don't know, I hope this will really bring things together for you about how this actually works and what it actually is. I'm going to rewrite this, and I encourage you to do the same thing. I'm going to rewrite this as the integral from a to b, but instead of writing v of t, I'm going to write v of t as a derivative. Velocity is the derivative of position. And so can we say maybe x would represent the position, like it's something moving horizontally or something? So instead of writing v of t, I'm going to write dx dt. Make sense? And the dt that was already there, I'm going to leave in there. It didn't go anywhere. So instead of velocity, I wrote dx dt. What would happen with the dt's? They would cancel out. And what does the integral do to dx? In other words, what is the antiderivative of dx? It's just x, right? 1x, if you will. So check this out. If I were to write this equals, integral from a to b of dx, I could then say this is equal to x of b minus x of a. Let's think about what that is. If x really is a position, then x of b, wouldn't that be the position at like time b? And x of a would be the position at time a. Subtracting them, what does that give us?
The displacement.
Displacement. There we go. So this is actually an important term. The definite integral of velocity is what we call displacement. It is the change in location, or the change in position. So that, if you think about it, isn't velocity the rate of change of position? And so the definite integral will just give you the amount of change of position. Go back to the overall principle. The net change theorem says that the definite integral of the rate of change gives you the net amount of change. Since velocity is the rate of change of position, then the integral, the definite integral of that will give you the amount of change of position. So integrating takes you from rates back to amounts. Make sense? Okay. Let's talk about a leaky tank. Considering units here, what kind of units do you think would go with a leaky tank? Gallons per hour, right? A rate-wise, gallons per second, gallons per hour, gallons per minute. Hopefully it's not a real high rate if it's gallons per second, right? That would equal a flood in your basement or wherever.
Could just be like,
Could be a tiny number, sure. Agreed. But per second, if you're going to go ahead and use per second, that makes me nervous, right? Well, otherwise, why would you use per second, right? I don't know. Hopefully it's not too bad. But the way this would work here, a leaky tank, definite integral from a to b of L of t dt. What this would give you is the amount that leaked from the tank. The amount that leaked from the tank from time A to time B. What would the units be on the amount? Gallons, perhaps, right? Yeah. Units-wise, check this out. Let me show you. I didn't show you on the other one how the units would work. Let's look at it from this perspective. Integral from A to B. You guys said like gallons per second. So let's just say L of t is measured in gallons per second. And then dt would have to be measured in seconds then, right? And so the seconds again would cancel. And you're going to end up with the amount of change of gallons. Your units are simply going to be gallons at B minus gallons at A. It's going to give you the net change in the number of gallons, like how much it changed. It's not going to tell you how many are in there. It's going to tell you how much the amount changed. So once again, definite integral of a rate gives you an amount of change. Okay. General principle, integral from a to b of rate dt is going to equal the net amount of change. So we're going to do a few examples. Some of these are going to range from conceptual and arithmetically easy. Some of them are going to be challenging on the arithmetic, and we'll use a calculator perhaps. But we'll do some examples here. So take a look at example number 1. Will you read it? It's about gasoline flowing out of a storage tank. Gasoline flows out of a storage tank at a rate of R of t gallons per hour. The graph of R of t is below. If the tank contained 150 gallons of gas at time 0, write an expression for the amount of gas in the tank at time t equals 3. Can you see the little tick marks on the graph? 1, 2, 3. So 3 is at the far right end. From left to right, the areas between the graph and the t-axis are A, B, and C. So I'm going to go ahead and label those for you. You can label them on your page too. So there's A, there's B, there's C. So those are just areas between the t-axis and the graph. Okay, so I want you to think about this. We have this graph. This graph is of R of t. What kind of thing is R of t? A rate. Yet the question asks, write an expression for the amount of gas. So what am I going to have to do to R of t somewhere? I'm going to have to integrate it, right? It's a definite integral. What would the limits on my definite integral be? It'd be the integral from where to where? 0 to 3, right? Because we're talking about how many gallons were in the tank at 0, and then how much end up there at time 3. So I would start us off with this. I would say, how many gallons were in the tank to begin with? 150. So we're going to start there. And remember, this is a finer point that I think sometimes gets lost. So I'll say it again. The definite integral of a rate is not the amount that's there. It's the amount of change. So if you want to know the amount that's there, don't you have to know how much you had to begin with? And then you add to that the change. Okay, so I'm going to say 150 plus what you guys suggested, the integral from 0 to 3 of r of t dt. This will give us, this would be an expression for the amount of gasoline in the tank at time t equals 3. But let's take it one step further. Let's write our answer in terms of A, B, and C. And I'm going to leave that up to you. So take a minute or two here, see if you can figure out what happens with the A, the B, and the C, and we'll decide how you did. Hey, can I get a volunteer to say what they think? How could we evaluate that definite integral and incorporate the A, the B, and the C? Huh, interesting. No volunteers? You all feeling a little in the dark? Okay.
Wait,
So-
is this graph a velocity graph?
There is no velocity involved in number 1 whatsoever.
So it's just the amount?
It's what?
It's a position?
No. So it explains clearly what r of t is. It's just that there's no velocity. I'm not sure what you mean by velocity.
Okay, never mind.
So it says gasoline flows out of a storage tank at a rate of r of t gallons per hour. So r of t is a rate. And I don't know if that's what you were getting at. So all rates are not velocities. But I feel like you were kind of right, that you were trying to, you're asking me, well, I think you really should have asked me is this thing a rate? And the answer is yes, it is definitely a rate. Go ahead, yeah.
So like, you were taking an integral, you're just like finding like the actual like number. So can you just like replace like that, the integral of RT dt with just like minus A minus B, or minus C plus like B? Like,
Yes.
That's all you have to do.
And let's come around to that. Why can I do that?
Because it's like, that's like the actual like amount, right?
What does the definite integral find on a graph?
The area under the curve.
It deals with area under the curve. So that's why I gave you the areas, right? But what's the trick to this? Say again? What's the trick to the areas? Some of them are below the t-axis, aren't they? Some of them are below, one of them's above. So when it comes time, and you said it pretty well, I think, when it comes time to evaluating this integral right here, listen, do we have any idea what r of t is? Like analytically? We have no idea what it is. And so the saying that I would teach you here, remember the saying I told you in the first semester of if you can't differentiate, that's fine. Just find the slope of the secant line. I have another saying kind of like that. If you can't integrate, accumulate. Accumulate area. If you can't integrate, just accumulate area. Right? Something worth thinking about writing down, I suppose. Okay, so I'll write down what Noah said, and we'll talk about why it's a good thing. So this would equal 150 minus A plus B minus C. We can replace that definite integral with minus A plus B minus C, because doesn't the definite integral just work with areas? Remember, the definite integral is an infinite summation of little tiny rectangles, little skinny rectangles. We're finding areas. All we're doing is finding areas, and so I can use the areas on the graph to then find the value of the integral, because that's what it does. And so this would be the correct answer. If you were at 150 plus A plus B plus C, what concept are you missing?
Negative.
Yeah, the fact that something below the t-axis will integrate as a negative quantity as opposed to a positive quantity. Something above will integrate as a positive. Okay. There we go. Questions? We're going to keep working with this. Please, any follow-up questions at all? Happy to address. Okay, fair enough. Let's keep looking. Let's look at our next section here using displacement and total distance traveled. So flip over to those. And there we go. Okay, so displacement. We just talked about this a second ago. Displacement is the net change in location from the starting point to the ending point. So I've said this before, I'll say it again. Displacement could be useful, but it could also be pretty deceiving. For example, I'm guessing that you woke up in your bed this morning, right?
Yes.
And tonight, when you get home and after you do your homework and eat your dinner and do whatever it is you do, you'll probably end up in the same place you woke up this morning, right?
Yep.
So your displacement for the day is?
0.
0, because you started in the same spot as you finished. That does not tell the whole story, right? Because you could have just stayed in bed all day and had a displacement of 0, yet you're here. And so while your displacement for the day will be 0, your total distance traveled will not. Because you actually did move. Displacement's just not going to tell you that. So displacement is equal to the definite integral from a to b of v of t. Let me show you with a graph how this might look. And hopefully this will make sense when we compare these. So if this is a velocity graph right here, and let's use your day as an example. So let's say, when time is 0, your velocity is 0. So you woke up in your bed, hopefully not running instantly. Hopefully you woke up and you're pretty much just sitting there, right? You wake up, and as soon as you wake up, you realize, I got to get ready for the day. It's not Saturday. It's not Sunday. I got to go to school. It's early, all that stuff. You start moving, don't you? You take a shower, you brush your teeth, you eat your breakfast. You start moving. So we're going to say, hey, your velocity goes from 0 to, you're moving away from your bed. The distance between you and your bed is increasing, so I'm going to call that positive velocity. You jump in the car, you eventually get to school, you start slowing down, and let's say right about there you get to school. And we're going to say that as long as you're on the campus, you're in the same spot. I'm going to simplify it a little bit. And so, for the whole day, your velocity, we're just going to say is 0. Because you're here, right? You're on campus, you're in the building, you're not really going anywhere. Your velocity is 0. But then at the end of the day, maybe you have practice, maybe you have a homework, maybe you have like a Vespers rehearsal or whatever it is. Don't you eventually go back home?
Yep.
So as you go back home, isn't the distance between you and your house decreasing? So your velocity would be negative. And so we would say, down here somewhere, here's your velocity. Maybe you just go straight home. Maybe you don't do any extra errands or anything like that. So, the curve of you going home is about the same as the curve as you coming here. Make sense? Yes? So if I accumulate the area, let's think about how would you describe this area right here? That's positive area. So we would say that that's positive displacement, right? And then, if you look at this area right here, this area would be negative. And assuming that you took the same route home as you did to get here, wouldn't the area below the t-axis be the exact same as the area above? It would just integrate as a negative because it's below the t-axis. So if I took this right here and said, all right, integral from, let's say, 0 to 10, integral from 0 to 10 of v of t, what would I get? If the area above and the area below are exactly the same size, if you integrate, you should get 0, right? And so this would illustrate your day, wouldn't it? From a displacement perspective, your displacement was 0. Kind of sad because you're doing a lot of work and going places. So maybe total distance would be a better way of describing your day. Total distance is the total amount traveled during the time interval. So we don't get too concerned about positives and negatives here. Notice how distance traveled and displacement, they look very similar with the exception of what? What does absolute value do? Yep, anything that was negative becomes positive. Everything becomes non-negative. So if I take the same graph and I say, you know what? I want to find my total distance traveled. My graph is going to look a little different. It's not going to be the graph of velocity. It's actually going to be the graph of speed, which is the absolute value of velocity. So parts of this graph will be totally unaffected by the absolute value, right? The first part, totally unaffected because it's already positive or non-negative. And so this first part, I'll do my best to replicate that shape. It's going to look exactly the same, totally unaffected. But that loop that was below the t-axis, the absolute value is going to take it and reflect it above. And so it's going to look something like this. And so now when we think about area, if we're going to integrate, if we say, integral from 0 to 10 of absolute value of v of t, it's certainly not going to be 0, is it? What can we say about it for sure? It'll be positive, right? It'll be some positive number, which is clearly different from 0. This would tell you your total distance traveled. Your car has an odometer. It does not have a displacement-ometer, right? Because what if your car, like the little numbers, that not the speedometer, but the little numbers that tell the mileage on the car, what if it was a displacement-ometer? How could you make your displacement-ometer be 0? Go back to the factory. Go back literally to where it was made. you just drove it back to the factory, whether that be in the US or Japan or France or Germany or wherever your car came from, the displacement-ometer would be 0. So if you ever wanted to sell your car, shouldn't you just take it back to the place that it was made? It's got 0 miles. It's mint, right? Perfect condition. Of course, that's exactly why they have an odometer as opposed to a displacement-ometer, because we're more interested in total distance traveled in a case like that rather than displacement. They both have their uses, but that's why you have an odometer. Okay, so we're going to do some examples with that. Make sense? Okay, so flip on ahead there to the next set, and get your calculators out too. We're going to use a new feature on your calculators. This should be a pretty quick setup for you. It says the velocity of an object moving in a horizontal pattern is equal to v of t right there, measured in feet per second at any time t. And question A says, what is the displacement of the particle on the interval 1, 5? And part B says, what is the total distance traveled on the interval 1 to 5? And then notice at the end it says, use math 9. So here's what I want you to do. I want you just to simply set up the expression. You could definitely evaluate the expression, but I don't want you to evaluate it by hand. I just want you to set it up, and then on your calculator, literally push math 9. And I think most of you will see the magic just happen. It's pretty cool. Okay? So please set it up. We'll talk about what you need to write down with something like this and how you could use math 9 to evaluate it very quickly. Okay? Ready, set, go. Please do A and B here. We'll give you just a couple minutes to set these up. We'll talk about math 9. From a setup perspective, here's what you need to have. Say for part A, it asks for displacement. So what you'd need to remember there is that displacement is the definite integral of velocity. So here's all you'd really need to write. If you wrote integral from 1 to 5 of v of t dt, you can write down what v of t is. You can put the whole t cubed minus 10t squared, dot, dot, dot. You can put that in there if you want. But since we already know what v of t is, if you just want to write integral from 1 to 5 of v of t dt, you're okay with that. That's totally fine. Now when it comes to evaluating this, this is where the magical stuff happens. So I'm going to, let's see here. I'm going to flip screens on you. Yeah, I want to do this. So with math 9, here's how it works. On your calculator, what you're going to do is this. You're literally going to just push math 9. And if you have the new operating system, which I think most of you do, this will do a numerical definite integral for you. And so if you get this new operating system, it's pretty straightforward. It's pretty user-friendly on how to enter things. The lower limit was 1, wasn't it? So I'm just going to go integral from 1 to 5. And then what I put in there is I put in v of t. The calculator will do the antiderivative. It'll do all the work for me. I just have to plug in what I wrote down. So what was that? Was that t cubed for the first term? You're going to have to help me out here.
T cubed.
So t cubed
Minus 10t
minus
squared.
10t squared
Plus 29t.
plus, you said 29t?
29t.
29t, and then what was the last term?
Minus 20.
Minus 20. And then the last thing we do is we have to give the differential, so it's dx. I know it's dt, but it's going to automatically, unless you're in parametric mode, it'll automatically give you an x for an input. So you hit that right there, and then all you got to do is hit enter. 10.6 repeating, it looks like. So let me just say this. It's a bold thing to say, but I think it's true in every case. If the calculator's active, and you got to find a definite integral, and you don't use math 9, you're being incredibly foolish. If the calculator's active, now what does that imply? Sometimes the calculator won't be active. So you still need to know how to do FTC 1 and 2 and be able to actually evaluate a definite integral. But if the calculator's active and you don't use this, you're definitely wasting your time. Guys, can I show you what you need to write down?
Yes.
Okay, so if you are doing a quiz and you had a question like A and you were on top of it, you're like, oh, I can use math 9. Let me use that. And here's what you wrote down.
Ooh, wow.
You get nothing.
Nothing?
0.
Not even a point.
Not even a point.
Half point.
Even if you put feet, you get nothing.
you have to show what you did. And here's how you show what you did. It's what we wrote down earlier. You simply have to write this. Show me what you put in the calculator by writing integral from 1 to 5 of v of t dt, and then you can put 10.666, whatever it was, feet, and now you get full credit. So you must show the definite integral that you used. Listen, that's a conceptual point, isn't it?
Yeah.
You're saying, hey, I know what to do. The calculator did all the dirty details and arithmetic and all the stuff that I'd rather avoid, and I get that. There's my answer. It's okay to do. So probably a 2-point question. The only way you could conceivably get one of the two is if you set it up, if you write this down, and then somehow your little fingers push the wrong buttons. You could get 1 out of 2 in that case, but if you just write answer, you get nothing.
I have a question. For the 10.666 repeat, did you just do 10.6 and then could you do the 1 over the 6 and then repeat? And would you count that?
Yep. Okay, and then for part B, it would be the definite integral from 1 to 5 of absolute value of v of t dt. You guys all okay doing absolute values on your calculator? Do you need to see this? Guys, that was a question. Yes or no? Do you need to see this?
Yes.
Okay, I'll show you. So the way you do this would be to go back to the calculator, and we just go math 9, and we go integral from 1 to 5, just like before. And then where you find absolute value is you go math, and it is num. Yeah, math number, I think it is. The first option is abs, that's absolute value, so you select that option, and it automatically gives you the little absolute value bars. And then you put in what you had before, so x to the third minus 10x squared, so on and so forth. And just like before, once you get to that point, what's the deal? Delete x squared, there we go. Minus 10x squared plus 29x, minus 20. Okay, so did any of you do this? Did you get a different number? You did get a different number, so let's see what I get. 11.8333. So we'll go back here to the notes, but let me ask you a question while I'm doing that. What does that mean that the total distance traveled and the displacement are different?
That means it went negative at some point?
Yeah, so in other words, the object did what? If it went negative
Lost.
and it used to be positive, it did what?
Critical number?
Because the object, physically speaking, did what? It turned around. It went from a positive velocity to a negative velocity, or vice versa, right? Had to have, because the displacement and the distance traveled are different. Okay, so as far as what you need to write down, again, I just want to reemphasize this to you. You'd want to write down the definite integral from 1 to 5, absolute value of v of t, dt is equal to 11.833 feet. And at that point, you have written down what you intend to do, like you've shown the concept, you get that. Use the calculator to evaluate that, full credit, right?
Can displacement be negative?
Yes.
Yeah. Okay, but distance.
Distance will always be non-negative.
Okay.
Could be 0, right? But it'll either be 0 or positive.
Okay.
Okay, final question for the day is C here. We'll get a chance to repractice the Math 9 thing again tomorrow. We'll probably warm up with that. So it says here in part C, if the particle is at position x equals 4 when t equals 9, find an integral expression for the position of the particle when t equals 20.
All right.
Let's boil this down. Hey guys, let's boil this down into simple thoughts. I'm telling you where it used to be
At t equals
when t equals 9.
Yeah.
And I want to know where it is in the future. So guys, listen. What is the piece of information that's missing? I told you the old position, and I want the new position.
The x of the new position.
Well, yeah, that's the ultimate goal, but what information do you need to get from,
The equation.
to get from where it was before to where it is now?
Like the integrated original equation.
Integrated original, because the original equation is
The velocity.
velocity, and the definite integral of the velocity is displacement, amount of change of position. Be really careful. I want to say this again. If I say the definite integral of velocity is, and you respond with position, you are incorrect. It's the change in position, right? There's a big difference. Listen, the football game on Saturday. If somebody runs for 10 yards, listen, if somebody runs for 10 yards, does that mean that they are on the 10-yard line?
No.
Not necessarily. If somebody runs for 10 yards, that means that they change location by 10 yards, right?
Yep.
Doesn't mean they're at the 10-yard line. At the 10-yard line, that is a position, isn't it? Ran for 10 yards, that's a displacement. They're related, but they're not the same. Does that make sense? So if I say definite integral of velocity, please don't say position. Say change in position, because they're different. Okay, so I know where this particle started. It started at x equals 4. So I'm going to say for my final position, 4 plus. So I know that I started at 4. I want to add to that the change in position. Think about it. If you start at 4 and you add the change, don't you get where you finished? Okay, so let's think that over. How do I find the change in position?
11 times. Or I guess you do.
I don't know where you're getting the 11 from. Oh, from t equals 9 to t equals 20?
Yeah.
Okay, let's go back. How do you find change in location if what you have is velocity? You got to integrate. So here's what you would do. You would write the integral from 9 to 20. Integral from 9 to 20 of v of t dt. You started at 4, and you add to that the change in position. So for example, right now, I'm about 4 feet from the door. So I'm at position 4. Right?
Yeah.
I'll mark my position. Position 4 right there. If I move around, maybe I go back and forth a little bit, who knows, I'm pacing or whatever. If I end up over here, and my change in location is 10 feet, what position am I in right now? 14.
Yeah, you still have that 4.
Say again?
You still have to add that 4.
Still got to add the 4 because that's where I started. Let me ask you one final question. In what situation would my displacement and my position be the same?
When it's only positive.
What about, say again?
When I start at 0. If I start at 0, will my displacement equal my position? That's the only situation, right? If I start anywhere other than 0, my displacement, my position will be different.
True.
Okay? All right. We'll keep at this tomorrow. Good job. I hope that worked for you. If it didn't, there's a video. Enjoy.